Hello and welcome to another IoT Central webinar. I'm David O'Hara and I'm the Managing Director at IoT Central. I'd like to start by thanking Ground Control for sponsoring today's event. Today's webinar is the third in a six-part series. It's titled Demystifying Satellite IoT for Cellular Specialists. Now I'd like to introduce our speakers from Ground Control. Drew Jackson is the Director of Operations and Technical Pre-Sales, and Oliver Potter is the COO. Gentlemen, when you're ready, let's get started.
Thank you, David. It's great to be here again with IoT Central. This is the third of our series of 6 webinars with IoT Central. So please look out for the other ones in the series. Today, we're going to be talking about satellite IoT, really through the lens of a cellular IoT specialist. So we're making the assumption that a lot of people have got cellular IoT projects and they may be then extending that into the satellite world. First thing we're going to talk about is data optimization. So using satellites uses battery and it's expensive because satellite networks are expensive. So really talking about how you reduce the amount of data you send and optimize that. We'll talk about interoperability. Now this is a big one really from cellular IoT side. We'll talk about both the sort of TCP/IP, sort of plug and play with a format you're probably familiar with using cellular IoT. But we'll also talk about some other messaging standards which really help bring a much greater degree of efficiency in both the network and cost. We'll talk about coverage. Clearly, you're using satellite because you want global coverage, but there are still some considerations there that we'll talk through. And then finally, power consumption. So a really important point here is we're assuming, or quite often, most of our devices aren't plugged into power. So they're operating off a battery with a very long life or a battery and solar panel. And so again, managing power is a really important thing in the satellite space. So let's jump straight in. Data optimization. So really a few considerations here. So satellite networks are expensive. They require a rocket to put the satellites into orbit around the Earth. And clearly a rocket is somewhat more expensive than putting up a mast in the bottom of a field or on a building in a city. And as a consequence, the data or the per megabyte price is more expensive than cellular and structurally will always be more expensive. I can't see a reason why ever in the future space and satellite would be cheaper. So we need to optimize our data to make sure we've got cost in the right place. And the really good news is here, and Drew will talk about this in a minute, is actually what we find is there's a hideous inefficiency with how data is often used kind of broadly on the internet. We're all used to loads of unlimited capacity, and actually we can help get the right information consolidated down, and therefore the cost is much less than you think it might be. The second thing here is the power consumption, which we'll have a whole kind of section on a little bit later. But the less data you send, the less time you're transmitting to a satellite, the less time your device needs to be awake and on, and therefore then the battery can be smaller or the solar panel could be smaller related to it as well. So a lot of things here that can really help reduce the overall cost and implementation complexity around this. But let me hand over to Drew, who's going to talk a little bit about data and information.
Thanks. Yeah, I think you touched on it there a little bit. I think that the key thing here is the difference between data and information. Most people, I think, conflate the two things and think about them in the same way. And I think it's really important to split them up. And so it's best to think of data as the raw zeros and ones that are generated by sensors and systems, and it has no context. Whereas information is the thing that you get out of data when you've applied context and you've interpreted the data. And so the industry's moved more towards, well, let's just send all the data and then we can interpret it and process it at the other end, where we've got loads of cheap storage and loads of processor capability to do that work. For example, you could have a cheap temperature sensor, and what we're looking for, the information that we're looking for out of that sensor is the temperature. But quite often these days it will transmit a load of information about its firmware version, its software version, its ID, what protocol it's using, how often it's transmitting, a load of configuration settings. And what we really want out of it is one tiny piece of information. What we've moved on to here with this slide is giving you some examples of different ways you can use edge computing to bring about that data optimization we talked about. So the easiest thing to do is to look at the vast amount of data we're sending and what do we actually want out of it. We can compress it either using some standard off-the-shelf algorithms. We can reduce it by looking at the data and just sending the parameters that we want, or we can perform some small amounts of processing and interpretation on it. We can look at the data, average it, reduce the amount of how often, the frequency that we're transmitting the data. So that's sort of step one on the ladder. Upping that sort of edge computing capability, we could decide to report by exception. So we could say we don't want to know every second that this temperature sensor puts out a temperature. What we actually want to know is when it changes. And so we say, okay, well, tell me when the temperature increases by 1 degree. Don't tell me every time it's the same. And again, that usually creates a massive reduction. The next one along is defining data priority. So in some of these protocols, like MQTT, for example, you can define different priorities for different data sets. And so we could say, well, for this lower data priority, I just want you to batch it up. And then when a high data priority packet is generated, then send it all together. And finally, you could decide to move a lot of the intelligence to the edge, into the field where the sensor is, and you could interpret and analyze the data while you're collecting it. So instead of sending the data back, we could what information are we looking for out of this data, and then what action is that going to have? And in the temperature example, maybe we want to know when it's hot, and we can define hot as above 30 degrees. And so we don't send any temperature data until it breaches this threshold, and at that point we send an alert to someone, something, actioning something. And so in that way, you're moving a huge amount of the intelligence into the field and massively reducing the amount of bandwidth you need. One of these examples is a customer who's gone and connected an off-the-shelf weather sensor. It spits out a serial string, temperature, humidity, pressure, whether it's raining, how much it's raining, etc., etc. And what we've done is connected our RockSense device. This is based on Iridium's SPD technology, short burst data, so very small packets of data. And what the RockSense does is it moves quite a bit of intelligence to the sensor side. We look at that serial string, we pick out some of the parameters. They're not interested in all of the parameters that are being generated. And then we average a 10-minute window every hour, and then we send the average of that result. And so that significantly reduces the amount of data that's being sent while keeping all of the information. Another one very similar. We have we have some bits of equipment attached to loggers that are generating huge amounts of information, and these loggers attached to these climate sensor bits of equipment, they're designed to run on cellular, and so they have a heartbeat that runs every 5 minutes, and that really generates a lot of unnecessary data and therefore cost. The equipment is produced by someone big enough that they're not really interested in changing their hardware to suit a small section of their customer base that doesn't want it on cellular and wants it on satellite. And so what we did with our Rock Remote device that they've got it plugged into is we implemented a timed firewall. So the device is capable of handling a network loss with cellular. So we remove we bring the firewall up and stop it from being able to communicate over the satellite network, at which point it sits there and batches up its data, including its heartbeat data. And then we bring down the firewall and allow it to transmit once a day. We get it all in at once. So for that IP style of connection over satellite, that's much better. There's far less toing and froing, and we get it all in one go. That might not be ideal for everybody, because you're still, we're still sending the heartbeat data and it's all sent at once. But for this specific customer, it was such a small amount of data when batched compared to the data set that they were, interested in, that it didn't really matter. So that was, another way of sort of batching up and controlling the data flow.
Great. So next section, we were going to talk about interoperability. So most or many of our customers talk to us having already rolled out something in Cellular. And in Cellular, you're typically using TCP/IP. And the good news is there's some really great services out there on satellites that do support TCP/IP, so it makes it much more plug and play. So there are things like Iridium's Certus 100, 200 and 700 service, or there's the Inmarsat BGAN M2M service as well. So kind of really good services, global coverage, offering TCP/IP. The other side of it, which we're really going to introduce a bit more in a second, is messaging services. So in the TCP/IP world, there's a lot of headers, there's a lot of overhead, but brilliant for it to be plug and play, and particularly brilliant for sort of a kind of a real-time conversation between the server and the device. But many things don't need that, and you can be much more efficient with messaging services. So Iridium have their SPD service, so their short burst data, and they've recently launched IMT, so Iridium Messaging Transport. And that's a much bigger message. So SPD messages are smaller, and IMT messages that go up to 100 kilobytes, so much bigger. And then there's Inmarsat, also have their Inmarsat Data Pro, so their IDP service, and they're also looking at an OGX service as well, which is like the same migration from SPD to IMT, but on the Inmarsat side. So there are really good options out there on the messaging side as well. So I'm going to hand to you, Drew, to just talk about TCP/IP and messaging, some of the considerations there.
As you touched on, the TCP/IP, everyone's familiar with. The satellites, they have a limited bandwidth because of their limited power. They're set up there running on solar, and so what the constellations did was they looked at the most efficient way to move data across their network. And while they need to provide a TCP/IP connection for people, some people just need that. The alternative is this packetized messaging protocol that they have, where you bundle your data up into discrete packets and just send it one at a time at the satellite, and that allows them to, they can multiplex you with everyone else who's operating like that, and it makes it much more efficient use of their bandwidth on the satellite. And as your system, then it's a really efficient way of moving data.
I mean, we actually recorded a webinar a few weeks ago on TCP/IP versus messaging. I think it's webinar 2 of the 6 that we've done, and our CTO Rick Searle talks in depth about TCP/IP and messaging here. So if you really want to explore this in some depth, go back and look at that one. A lot of you will be familiar or already be using MQTT, and we've got a neat little solution we've put together where you are leveraging messaging. So you're leveraging Iridium's IMT, but you're using MQTT at both the sort of the server end and the device end. So in this slide, we'll just illustrate it. So on the left-hand side, the device in the field connected to lots of sensors. We put an MQTT broker on our Rock Remote rugged device. So all of the sensors think they're talking to the MQTT broker. We split the MQTT broker in 2. So we also have the other half of it in our Cloud Loop cloud platform. And between those two, between the device and the Cloud Loop MQTT broker, we're using Iridium's messaging service, so IMT. And so that's very efficient, none of the overheads associated with TCP/IP. And then your client end and your application thinks it's talking directly to the sensors, but there's this magic happening in the background that makes the transport through the satellite network much more efficient than it would otherwise be. So it doesn't have to all be heavy engineering and using IMT directly. There are some clever solutions like this one we put together to enable you to leverage it.
Yeah, so we had two customers who they had systems using MQTT and another one using FTP. Both standard protocols, but sit on top of the IP layer usually. They could have just put, an IP satellite connection in the middle and plugged it in, and it would have just worked. It just would have been expensive. And so with both of these customers, they were actually part of the reason why we implemented the MQTT and FTP over IMT features that we have, so that we could aid them with the implementation of this system into their existing systems. And so with the FTP one, we've got an FTP file server running on the Rock Remote. You connect to it as you usually would on the sensor side. It listens to that FTP traffic on the local network coming in, and then we package it up. We send it over Iridium's IMT transport layer. Comes into Cloud Loop Data. You can define an endpoint, and it just arrives on your server as a FTP packet as you would expect it to. So super straightforward, really easy, and it meant that they didn't have to change anything. The systems were already up and running. This could just slot in the middle and allow them to go to a much more efficient satellite implementation of what they were trying to do. Also very useful for, quite often we get approached by companies where they've done 90% of their rollout, on cellular, where they could be using these protocols, and we need to finish that last 10%. They don't want an entirely new system. It has to work with what they've got already up and running. So yeah, this is a great example of that.
Cool, thanks, Drew. So should we talk about coverage? So I guess the first thing is you'd think, well, satellites, they're everywhere. You cover the whole world, right? So that's true, but there are definitely some considerations there. So cellular probably covers about 15% of the world's surface, so you've got 85% of it to go. There are really kind of two concepts with satellites. So there are geostationary satellites and there are low Earth orbit satellites. So the geostationary ones are a long way away from Earth, I think about 36,000 kilometers away, and they rotate around at the same rate that the Earth rotates. So they're always over the same bit of land. And then there are LEO ones, which are much, much closer to Earth, and they spin around the Earth on a number of different axes. And therefore those satellites come over, and then the next one comes over, and then the next one comes over. So you always have a satellite, or you could always have a satellite coming over from a LEO perspective. So breaking those down, the GEO ones are brilliant. Inmarsat and Viasat have a great constellation that covers nearly all of the world. Because they have to follow the sort of equatorial orbit around the Earth, they don't brilliantly cover the poles. So if you're going to the far extremes north and south, and you want your device or your asset tracked or monitored in those areas, might not work, but certainly kind of around most of the world works really, really well. Then you have the LEO services. So the best and the preeminent one in the IoT space is Iridium. So they have 66 satellites that go on a north to south orbit sort of around the world, and they have truly global coverage. And actually, because they cross at the poles, they have an incredible coverage at the poles, but brilliant coverage all over. The second consideration, once you kind of thought about GEO and LEO, is, well, how quickly do you need your data? Because while those two networks we've talked about are absolutely real time, you're getting your message back in a couple of seconds. Some LEO networks only have 1 or 2 or 3 or 4 satellites up there, so then you have to wait for it to come back round again. So you might have an 8-hour or 12-hour wait, just depending on the kind of service you've got there. And then the final piece on the right here is, what's the precise location? So one of the advantages of the LEO satellites is, because they move over, if you've got a view of some of the sky, at some point you'll probably get a connection. But if you're behind a big hill and the geo satellite is on the other side of that hill, if you're trying to connect to a geo, then it just wouldn't work in that circumstance. You would then have to think about, can you move the location of your device if it's static, or can you, live with it being temporarily disconnected while it goes behind a hill or behind something like that. So these are absolutely some of the kind of considerations we've got there. And Drew, we were going to talk about a utility customer, weren't we?
Yeah, so this kind of, it talks to the coverage, point that we're on at the moment, but it also sort of talks about the interoperability and also some of the edge processing and power, and brings it kind of all together, really. We've got a couple of utility customers where they're trying to monitor a good number of things over, let's say a square kilometer or something. One example may be a dam in a valley, where they're trying to monitor different points of the whole system, and quite a lot of those points won't have a very good view of the sky at all, because either the dam's in the way, or the valley walls are in the way, or another building's in the way. And so what they tend to do is combine a couple of different technologies, and so LoRaWAN is a great technology for combining lots of IoT a lot of people listening to this will probably be quite familiar with LoRaWAN because it's big in the cellular side of things, and so let's say they've got 10 different sensors distributed in this facility. They can use LoRaWAN to collect up that information from all the different sort of obscured sites on that bigger system, and then go back to a LoRaWAN gateway, which you can connect up to Rock Remote. Some of them, also have MQTT from LoRaWAN, so that gateway will put it over into MQTT, and then we'll do MQTT over IMT. And so, from a coverage perspective, what it's doing is it's using the right technology to collect all of the data locally, and then we're sending it to somewhere where we can install a satellite device with a good view of the sky. We've got a bit of edge computing there, which is sending the MQTT over IMT to reduce the overheads. And so, yeah, it's a good example of a few of those points that we've made coming together for one of our utility customers.
Yeah, and equally, we have some customers doing a similar thing, but they're using a geo network because they've got a fixed point in the sky and they can point at it. But
absolutely, yeah. If I mean, that's one of the major positives about geos is, if you can see the satellite, it's not moving. So if there's nothing dynamic in your setup and you can see it, then you'll always be able to see it, and so that can be very useful. Sometimes in very occluded locations, you might have a situation where you only have a very small open view of the sky, but it just so happens that in that hole there is a satellite. And so in that situation, it works well, whereas the LEO would only, pass over that very small hole, infrequently. So yeah, you just got to look at what you've got, your view of the sky, and that's where we help people do, site surveys and things like that, and figure out the best way to get things set up.
And I think it's probably worth a little bit of a segue just now, actually, Drew, just to talk about antennas. So the antennas that are connecting to these LEO networks are really quite small. They're the size of a large coffee cup that you might get from Starbucks, or even smaller than that.
Yeah, I mean, that'd be one of the bigger ones. Really, it depends what you're trying to achieve. But yeah, for the SPD that we touched on earlier, you're down to a 25 mil square patch antenna on the rock block. So those things are tiny, very omnidirectional. You don't need to worry about pointing it. Just give it a view of the sky, and it'll figure itself out. The Certus 100 ones are, as you say, sort of the size of a coffee cup. And then, generally speaking, the more throughput you need, the bigger the antenna gets.
Yeah, absolutely. So I mean, we cover many of these topics as we go along, but to kind of really try and help break it down, let's talk about power consumption. So we already talked about this at the very beginning, but on the data versus information side. But obviously, if you send less data less frequently, your device needs to be awake and in transmit mode less. So therefore, it's obviously using less power. that's a major thing. I think some of our our Certus 100 devices, our best ones, sort of sit in idle at 0.1 of a watt and then transmit at 7 watts. So keeping it out of that transmit state for as long as possible, kind of really important for long battery life off grid. Send less data, as we talked already about it from a kind of cost optimization perspective, but just reducing down to the kind of key, is it report by exception or whatever it might be, just again to reduce the amount of time the device is awake and having to transmit. We've talked extensively, obviously, about TCP IP and messaging, and there's the other webinar that you can kind of look about that one. But using messaging has less overheads, so for really small amounts of information, a much more efficient way of using kind of the battery you have on the device as well. So we have so many customers that use SPD who didn't believe they could use SPD because they thought they would have to have a TCP IP stream, but get absolutely everything they need in a really sort of power efficient and cost efficient package using SPD. And then the final kind of consideration is, like any mobile phone that's got 1 bar of signal, it has to work really hard to communicate with the mast. And one thing that is important is your antenna is at the top of your device or your asset. It's got a good view of the sky, and therefore it can operate much more efficiently than it would be sort of not pointing well to the sky. So kind of some key considerations there. Drew, should we talk about power and devices and considerations there?
Yeah, this is an interesting graph. It's mainly representative rather than sort of showing you exact facts and figures. But what we're trying to show here is the sort of progression that you go through for power, really, power versus bandwidth. And the reason most of the time we end up talking about power is because a lot of these IoT assets aren't able to just plug into something. If you can plug into something, then Starlink is a great system, but it is a big terminal and it uses loads of power. So assuming you can't plug into the mains and you've got some form of power restriction, and that may be a fairly generous power restriction. You may have quite large batteries, you might have quite large solar panels, and so you can afford to run things like the BGAN, Inmarsat's BGAN system, something like the Cobham 540, where you can have a nice IP connection up all the time, and it's not crazy power hungry. Sort of stepping down from that, you've got the Iridium Certus 100 really is the next one down, where you can run it on a battery and a reasonably sort of sized solar panel, but it's going to be too big for any sort of discrete installation. Down from there, the Rock Remote Mini is our new product, where we took the Rock Remote and really tried to optimize it from a power perspective, bringing that standby power down as much as we can, because as you talked on in the last slide, you're trying to reduce the time that we're talking to the satellite. So a lot of the time these devices aren't sat there transmitting, they're just in an idle state. So the vast majority of the power consumption comes from just the idle time in between transmissions. So a lot of the time your peak power usage when you transmit isn't that much of a consideration. It's how low does it go when it's idling or asleep. And then right at the bottom, super efficient if we're talking about drones and things that have a really limited power and weight requirement, then SPD is perfect because it's super low power when it's idling. Yeah, so that's kind of your spectrum of power versus bandwidth.
Yeah, no, I mean, it's great to show, and clearly what you can see how all of these concepts are kind of coming together to sort of help you just decide how you're going to kind of roll something out. You've got to consider the power and the cost and your view of the sky and everything that we've talked about.
Yeah, I was just going to say, usually it's kind of the right answer comes to you once you've figured out all of your parameters. There's not loads of right answers to pick from usually. There's a path that you'll end up going down depending on all of the things you just mentioned.
Yeah, that's great. We also did an SPD one for fracking tanks, didn't we, in northern Canada? Do you want to talk about that one for a
Yeah, we took our RockSense Sense device, as you say, built on the SPD modem, so fairly lightweight to start with. It's connected to a load of sensors measuring something on a fracking site. I'm not entirely sure what, but it was up in the northern part of Canada where geo wasn't possible. We were just too far north, so it needed to be a LEO. There's obviously long winter months there as well, so you needed a battery that could cope with the Canadian winter, and a solar panel to collect the energy through the Canadian summer. And so yeah, we put together a nice package for this customer where it's completely independent and can sit there working all year round collecting the sensor data. We do a bit of edge processing. We look at the data coming in, we average it, and then send it back to our Cloud Loop platform for them to consume.
Great, thanks, Drew. I think this is really bringing us towards the end of it. So we watched a webinar recently where Robbie Hamlet, who's the CEO of Teal, talked even in the cellular space that said just because it's a free lunch doesn't mean you should eat as much as you can. And he was talking about with narrowband IoT networks and some of the congestion that they're seeing in cellular, you absolutely have to, even there, look to optimize your data. And it's exactly the same in our world as we've talked about. So the example at the top here is one of our messaging positions. So it's one of our tracking positions, and on the left you've clearly got the human readable text, but you can absolutely compress that down by reducing it down to that kind of single 8-byte message.
Going back to the quote out of the cellular IoT space, I think it was fascinating that they're starting to consider this, because for ages it just wasn't a thing. I think it's the more that they embrace that, then the easier it gets for moving any of those systems across into the satellite space. So I think it's great that they're talking about it. And yeah, as you talk to that example on the screen there, what we're doing there is we're reducing it and stripping out some things, and then it's a vast reduction from 153 bytes down to 8. You can see how effective you can be just with a bit of bit packing. And
so I think we've talked about compressing data or making sure you send as little information or data as possible. So really focus on the information you want to send. We've talked about the interoperability. Can you do messaging? Can you be much more efficient, or do you want to need to stick with TCP/IP, or is there a middle way using MQTT, like we talked about with the broker in the middle? And then we've recently just talked about coverage and power, and all of these come together kind of to make a solution design. So as we've both mentioned, I think a number of times, we'll look at the solution that you need, where in the world it's going to go, what information you need to send, and then work with you in order to kind of design absolutely the best solution to make it cost effective, make it work on a battery powered device in the middle of nowhere. So before we close, Drew, any kind of final thoughts from you?
No, I don't think so. Come and talk to us. Yeah, as you say, we've been doing this thing for a long time. There's a lot of things to consider. We can help you figure it out.
Okay, great. Well, thanks. That's enough from us, and we'll hand back to you, David.
Well, this brings our webinar to a close. I'd like to thank Ollie and Drew for their insightful presentation and Ground Control for sponsoring today's event. You can view more webinars, including part 1 and 2 of this series, at iotcentral.io. Thanks for watching.